Okay, we're going to pick up with part 2B on the implicit differentiation class notes and lesson notes. And we went through example 1, 2, 3, discussing how we differentiate both sides, get all the dy dx's on one side. We looked at a graph. If we're finding the slope, we kind of want to reason with the graph. Does this look right? Do we have the right slope? Is it positive or should it be negative? Or considering graphs that we're not really familiar with, maybe you want to take this and graph it and see, let's put an xy point in that we know is on the curve and see if our derivative is correct. So now we're picking up with part 2b, and we take the derivative. We want to find the equation of the tangent line to the curve of x to the 2/3, y to the 2/3 equal 5 at the point 8,1. So we take the derivative of both sides of the equation. So on the left-hand side, we take the derivative of each term individually, and the right-hand side, the derivative of 5 is equal to 0. So we get 2/3 x to the negative 1/3. We're going to take 2/3 and subtract 3/3, so at negative 1/3. And then we have plus 2/3 y to the negative 1/3, and then we have to multiply by dy dx is equal to 0. So now we could multiply everything through by 3/2, and that's kind of convenient. If we multiply through by 3/2, we can then, of course, get rid of the constant factors, and it makes our job, because it's going to end up dividing out anyhow. So then we get the following. If we multiply the first term by 3/2, we get x to the negative 1/3. Then we get plus y to the negative 1/3, and then dy dx equals 0. So now I'm going to take the x to the negative 1/3 to the other side. So we have y to the negative 1/3 dy dx is equal to negative x to the negative 1/3. So then I've got dy dx is equal to negative x to the negative 1/3. These negative exponents are kind of a little irritating, and we're going to divide both sides by y to the negative 1/3. And now I'm going to bring this up here. Remember, we want to find the equation of the tangent line too. So we have dy dx, but I'm going to use one of those rules in algebra where we know our derivative is negative, but I'm going to flip the x to the negative 1/3 and the y to, so I'm going to make this y to the 1/3 over, remember, if you have a quotient and you have negative exponent in the numerator and the denominator, a to the negative n over b to the negative m, like so, then that's b to the m over a to the n, like that. So we're just using that rule, x to the 1/3. And then we can leave the negative out front, and then we can make this the whole enchilada as the cube root. I'm going to take a second with that. So that I could make this y over x and then to the 1/3 power. And you can just say that that is negative the cube root of y over x. So there's our dy dx. Now what we want to do is we want to be able to take this, sorry about that. Take this, and then we're going to evaluate this. So we want dy dx, and we want it evaluated at the point where it's 8,1. Okay, 8,1. So that's kind of easy, right? 8 is x and y is 1. So it should turn out to be, let me see. And, in the back of my mind, I'm thinking I really didn't have to do all this work with that. But 8, it's going to be the cube root, the negative of the cube root of y, which is 1. And, right, that's the cube root, right? So it's going to turn out to be negative 1/2. I'm going to just stick it out here, negative 1/2, right? Negative 1/2. So there's our slope. And we want the points, we want the equation of the tangent line, so it's just going to be y minus 1 in point slope form is equal to negative 1/2 times the quantity x minus 8. There you have it. There it is. There you go. And boom. Okay, let's try another one. So we're taking the derivative, and we've got to watch it because we got to use product rule with this. You notice how I've color-coded it here. So I'm going to go ahead, and I laid it out already. So we've got the first is x squared, first factor of that product rule, x squared. Then we take the derivative of y squared, which is then going to be 2y, but then you have to remember to use chain rule dy dx. Plus, then we have a y squared, and then the derivative with respect to x of x squared is just going to be 2x. Then we have minus here, the derivative of 9x squared is just 18x. And then you have the derivative of 4y squared, which is going to be 8y 8y, and then we have a dy dx on there. We have to use the chain rule with that. And then on the right-hand side of the equation, we have the derivative of 0, which is still going to be 0. We're going to get all of our dy dx terms together, but I'm going to write that as 2x squared y dy dx plus 2xy squared and minus 18x, and then minus the 8y dy dx. Just going to clean up that first term is equal to 0. Okay, everything nice and neat there. And then we're going to put all our dy dx terms together. So we have 2x squared y, and then we're going to subtract 8y, and that's going to be dy dx. And then we're going to take every other term that doesn't have a dy dx in it. There are two of them. We're going to take them to the other side. So if I add 18x, and I'm going to subtract 2xy squared from both sides, okay? So that's going to give me 18x minus 2xy squared. Remember, you're doing this to both sides of the equation. Okay, and then I'm just going to divide by 2x squared y minus 8y. And I have my dy dx. Dy dx is equal to. Now, I want to factor out a common factor here. So you don't have a common factor of x or y between all terms, but you do have a common factor of 2. So if I factor out a 2 in the numerator, it's going to give me 9x minus xy squared. And in the bottom, you can see you can factor out a 2 easily, 2. And then that becomes then x squared y, and then minus 8y. So canceling the 2, minus 4y, sorry about that. So we 4y here. Okay. And so that is really, I'm just going to erase these 2's. Bye-bye. All right, and there you go. There you have it. There it is. Okay. And then I wanted to see if I could fit one more example on this. I know this is, some of these take a little bit of time, just wanting to be careful with your algebra manipulations. Okay, and then on the next one, we have to find the second derivative. So if I take the derivative of the left-hand side, we're going to use the product rule with this. I'm going to leave the negative out front, and it's going to be first or second. Notice the 1 I just skipped by because the derivative of 1 is 0. I could put that in. First or second plus second as a y to first is just going to be 1. So the left-hand side is done. Now taking the derivative of the right-hand side, you get the derivative of x first, which is 1, minus the derivative of y, which is dy dx. Got to get all the dy dx's on one side, but I'm going to rewrite this one. I get a minus x dy dx. Then you have a minus y is equal to 1 minus dy dx. So I'm going to put the dy dx on the right. I'm going to add that to both sides. So that's going to give me a dy dx minus x dy dx. And then, so I added dy dx to both sides. And then I'm going to add y. I'm going to add y to both sides as well. So then I get is equal to, so I have both the dy dx terms on the left-hand side, and then I end up with a y plus 1 on the right-hand side. So then I'm going to factor out a dy dx, dy dx. That'll leave me with a 1 minus x factor is equal to y plus 1. So starting over here, we have our dy dx then easily is divided by 1 minus x. So I get is equal to y plus 1 over 1 minus x. And now I've got to get the second derivative. So I'm going to take the derivative with respect to x of both sides. And the notation kind of makes sense. That Leibniz notation is fantastic because it really helps us to understand when we do these kind of steps that when we're taking the derivative, notice that we have the derivative twice and then we have dx twice. So when I write the notation that Leibniz created, it was d2y over dx squared, and didn't bother putting the parentheses around it either. So now we're ready to do the quotient rule with this. So we have low, d high is just going to be dy dx. Low d high less high, y plus 1. D low is going to be -1. And that's all going to be over low squared. So it's going to be 1 minus x squared. You don't have to square out the 1 minus x either. So we get the second derivative, then dx squared is then equal to 1 minus x. And we're going to plug back in, we're going to plug in the dy dx here, which is y plus 1 over 1 minus x. It's kind of a convenient thing when you look at it. And then this is going to be, if you look at the minus and then you have a negative here. So we can actually make that, that's a double negative right there. Subtracting, then the negative becomes positive. So here we have the quantity y plus 1, right? So remember, we're finding the derivative, right? Hold on. So what do we have here now? Oh, this is a plus, right? Yeah, there we have it. There you go, 1 plus 1. All right, so then we have over 1 minus x, the quantity squared. So we can cancel our two factors here, 1 minus x down here. So we get 2 times, in the numerator, we're going to get the second derivative of y with respect to x is then equal to, in the top we get 2 times y plus 1 over 1 minus x, the quantity squared. There you have it. There it is. There you go. Okay, see if that makes sense to you. I'm going to have to figure out here. Let's take this down a little bit. Okay. All right, and let's see if we have time for one more here. So if we use the power rule, we're finding the derivative of the square root of x. So then we would have dy dx is equal to 1/2, and we could have just jumped right into 1 over 2 square roots of x plus 2. But we'll just do it like this, x plus 2, and to the negative 1/2 power. And then the derivative of the inside function is just going to be 1. You don't really need chain rule for this one. So we end up with 1 over 2, and x to the, it would be x plus 2 to the 1/2. And then we would write that derivative then as 1 over 2 square roots of x plus 2. So there you have that derivative. Well, we could also use implicit differentiation with this. And we could, what I would do then is I would take this and I would write it, I would square both sides, right? So on the left-hand side, we're going to get 2y dy dx is equal to, on the right-hand side, we're going to get 1. So we get dy dx, the derivative, is equal to 1 over 2y. Now, you guys know 1 over 2y, y is equal to the square root of x plus 2, boom, 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 x plus 2. And there you have it. You actually get an identical looking derivative. Now, there are times where you can get an equivalent derivative. It doesn't look the same at all, but it can be equivalent. But in this case, it turns out to be exactly the same when you substitute in your function. Okay, this is the end of part 2 B. And I'm going to pick up with finishing the rest of this lesson. Here I want to just drop this down. Finding the second derivative and then using implicit form versus the generalized power rule. So we'll pick up with the next problem, which has to do with an ellipse. And I wanted to go over that completing the square idea and the derivative, and then answering the question where tangent lines are horizontal or where they're vertical.